Usually, we're chasing the news cycle, looking at the latest article on tech trends or some flash in the pan study.
Right. What's hot this week?
Exactly. But today we're slowing down, we're dropping the anchor, we are tackling a monster.
A monster in the best possible way. A foundational monster.
Absolutely. We are tackling the Bible of the field. We're looking at artificial intelligence, a modern approach by Stuart Russell and Peter Norvig.
Yeah.
And I don't use the word Bible lightly here. I mean, if you have walked into a university computer science department in the last, 20 years, this book was there.
And it was on the shelf. It was probably the required text. It is the definitive text.
It's huge.
It really is. It's dense, it's comprehensive, and it's heavy. Literally and metaphorically. And what's so fascinating is that even though AI is moving at this just breakneck speed right now.
Every week, something new.
Every single week. A new model, a new capability. But the architecture laid out in this book, it's still the map everyone is using. It fundamentally shapes how we even think about machine intelligence.
And that is exactly why we're doing this. I feel like there's this massive disconnect right now. The public hears AI and they think of sci-fi.
HAL 9000.
Right. They think of robots with feelings, or they think of ChatGPT writing a sonnet about, I don't know, a dishwasher. But we're going to strip all that hype away today. We're going to look at the mechanics. How does a pile of silicon and electricity actually think?
And to answer that, you have to start where the book starts. You have to define what you're actually trying to build. And Russell and Norvig, they make this distinction right on page 1 that effectively changed the entire history of the field.
Okay.
They ask a simple but really a devastating question. Are we trying to build something that acts humanly, or are we trying to build something that acts rationally?
See, my first instinct, and I think the instinct of most people, is to say, well, aren't they the same thing? I like to think I'm a rational human being.
You would hope so. I would hope so too.
Oh.
But the book is actually quite funny about this. It points out that if your definition of AI is mimicking humans, you have a serious, serious engineering problem.
How so?
Because humans are messy. We're imperfect. We make mistakes. We get tired. We have cognitive biases. We forget things.
I feel seen right now.
I think we all do.
Yeah.
As the authors put it, not every chess player is a grandmaster, and unfortunately, not everyone gets an A on every exam.
Right.
So if you built an AI to perfectly mimic a human, you would literally have to program it to make math errors. You'd have to program it to get confused or to be biased or, to forget where it put his tar keys.
That is a great point. I mean, if I'm building a calculator, I don't want it to have a human day and tell me that 2 plus 2 is, roughly 5, depending on how I feel.
Exactly.
Yeah.
Exactly. So the field pivoted. The goal isn't artificial humanity. It's computational rationality.
Computational rationality.
And this is the core concept we really need to lock in for this whole deep dive. They define an agent, which is just the fancy term for the AI program, as something that acts to maximize its expected success, given what it knows.
Maximize expected success.
Yes.
Let's unpack that a little bit.
It just means it doesn't matter if the AI feels happy about winning the chess game. It doesn't matter if it has a soul or consciousness or anything like that.
Okay.
It only matters that mathematically it selects the action that gives it the highest probability of hitting its goal, whatever that goal is.
So we are shifting from psychology, trying to recreate the human brain, to something more like economics and mathematics.
Precisely. It becomes a problem of search, probability, and decision-making under uncertainty.
Yeah.
It's a numbers game.
So let's get into the gears of this. The roadmap for today is really interesting because it sort of follows the history of how we learn to build these things. We're going to look at how computers search for answers, which sounds simple, but is actually incredibly complex. Then we're going to look at why logic, good old true and false, actually failed AI for a long time, and how they had to pivot to probability.
The big pivot.
And finally, we'll look at how these machines perceive the world, how they see and speak in our messy, messy world.
It's the journey from the chessboard to the real world, from a perfect, clean environment to reality.
So let's start there, the foundation, the game. The sources talk a lot about early AI treating the world like a game, specifically a zero-sum game of perfect information. Why was this the starting line?
Because the real world is terrifyingly complex. I mean, just think about it. If you're a researcher in the 1960s or 70s, you can't simulate a city street.
No way.
There's just too much chaos, too many variables. Is it raining? Is the traffic light broken? Is a pedestrian going to jump out? But a chessboard is safe. It's a clean environment.
Clean in what way? What does that mean technically?
It means it has perfect information. That's a technical term. It means nothing is hidden. I can see your king, you can see my king. There are no cards face down.
No fog of war?
No fog of war. And it's zero sum. If I win, you lose. There is no win-win scenario. There's no negotiation.
It's a closed universe. Me against you, and the rules are absolute.
Exactly. And because it's a closed universe with strict absolute rules, you can, in theory, map out the future. And this brings us to the first major technical concept in the book, the game tree.
I love this visualization. It sounds so mystical, the game tree, but it's actually just, it's a map of destiny, isn't it?
That's a very poetic way to put it, but yeah, that's what it is. Imagine the current board is the trunk of the tree. From this state, I have, say, 3 legal moves I can make.
Okay. So branch A, branch B, branch C.
Right. Now, if I take branch A, it becomes your turn. And from that new board state, you might have 5 legal responses. So branch A splits into 5 smaller branches.
Okay, I see.
And then for each of those 5 branches, it's my turn again, and I have my responses. The tree just, it expands exponentially. Every move, every possibility is a new branch.
For a game like tic-tac-toe, I can actually visualize this in my head. You know, I put an X in the corner, you put an O in the middle, the branches split. But the book mentions that for tic-tac-toe, the whole tree is actually pretty manageable.
It's tiny. I think the number is under 363,000 nodes or states in total.
363,000.
Which, for a computer, even a slow one from the 80s, is nothing. That is absolutely nothing. It can generate the entire tree from the first move to every possible win, loss, or draw.
So it can see the end from the very beginning.
It can see every possible ending. It knows if I make this move and my opponent plays perfectly, I force a draw. If they make a mistake right here, I win. It's a solve game. A computer playing tic-tac-toe isn't thinking.
It's just looking up the answer.
Yes, it's just looking up the answer in a pre-computed database of the entire universe of the game.
But then we get to chess. And the numbers here just, like, they just melted my brain.
It is staggering. It's a completely different scale of problem. This is where the brute force method just dies a spectacular death.
So what's the number?
The book mentions that the game tree for chess has roughly 10 to the power of 40 nodes.
10, with 40 zeros after it.
Yes, 10 to the 40th power. To put that in perspective, that is vastly, vastly more than the number of atoms in the known universe.
Okay, so we can't map the whole tree. We can't see the end of the game from the beginning. It's not possible.
It is physically impossible. You could turn every atom in the entire solar system into the fastest supercomputer imaginable, let it run for the entire age of the universe, and it wouldn't even make a dent.
Wow.
So the AI has a crisis. It wants to act rationally. It wants to choose the move that leads to a win, but it can't see the win. The winning node is trillions and trillions of branches too far away.
It's like driving in a thick fog at night. You know your destination is San Francisco, but you can only see the headlights of the car 20 feet in front of you.
That is the perfect analogy.
Yeah.
So how do you drive to San Francisco in the fog? You can't see the city, so you need a substitute. You need a proxy.
A signpost.
A signpost. Something that tells you, I am roughly heading in the right direction.
And in the book, they call this the heuristic or the evaluation function.
Right. So since the AI can't see, checkmate, the final destination, it looks as far ahead as it can. Maybe 10 or 12 moves down the tree, and then it just stops. It has to.
It hits its search limit.
It hits its search limit. And at that point, it looks at that future board state and asks a simple question. Does this look good?
But how does a computer know what good looks like without seeing the end? What does good even mean to a machine?
It counts. A very simple classic evaluation function for chess is just material value. It assigns points to each piece.
Okay. So a queen is worth 9, a rook is worth 5, a lowly pawn is worth 1.
Exactly. The AI looks 12 moves ahead, and it calculates a path where, at the end of that path, its pieces on the board add up to, say, +5 more than the opponent's pieces.
Yeah.
And it assumes this path is good. It assumes that having more pieces, well, that usually leads to winning.
Usually. That's the catch, isn't it? That's the whole ballgame right there.
That is the entire catch. A heuristic is a rule of thumb. It is an educated guess. It is not a guarantee. And this leads to one of the most fascinating and, frankly, most human-like problems in the book, the horizon effect.
I loved this part. It sounds like a sci-fi thriller title, The Horizon Effect.
It really does.
Yeah.
And it describes a specific pathology, a mental illness, almost in AI reasoning. So imagine the AI is looking ahead. Its search limit, its horizon, is 10 moves.
Okay. The edge in the fog.
The edge of the fog. At move 8, deep in its calculations, it sees something terrible. It sees that if it follows this path, it's going to lose its queen.
Oh, no.
The evaluation score plummets to 99. The AI hates this. It's programmed to maximize its score to maximize success.
So it looks for a way out, any way out.
Yeah. It starts searching frantically for any other move, any other path that prevents that queen loss at move 8. And it finds one. It realizes, hey, wait a minute. If I sacrifice this worthless pawn over here, and then I throw my bishop away over there, it complicates the game.
It creates chaos to distract from the problem.
Precisely. And in that chaos, the opponent's inevitable queen capture gets delayed. Instead of happening at move 8, the timeline shifts, and the capture is now scheduled for move 12.
But the AI can only see to move 10.
Exactly. The disaster falls off the edge of its world. The AI looks to its horizon at move 10, sees it still has its queen, the score looks great, and it thinks, perfect, I solved it. I'm a genius.
But it didn't solve it. It just pushed the inevitable death a few steps into the dark, and it paid a high price to do it.
It actually made the situation much, much worse. It sacrificed a pawn and a bishop just to delay the inevitable by 2 turns. It's procrastination, but for a machine.
That is deeply, deeply relatable. Oh, completely. I feel like I do that with my own life. If I just don't open this stressful email today, the problem is pushed past my mental horizon for the weekend.
Yes.
I am maximizing my expected happiness for Saturday at the cost of total disaster on Monday morning.
You are suffering from the horizon effect. We all are. It is a fundamental weakness of bounded rationality. The machine is acting rationally within the limits of its search, but the overall outcome is deeply irrational because of what it can't see.
So how do they fix this? Or, how do they make the search better so this happens less? The text mentions pruning, specifically something called alpha-beta pruning.
Pruning is such a great gardening metaphor for this. If you're searching a massive tree of possibilities, you quickly realize you don't need to explore the sub-branches of every single move.
Okay.
Suppose you're looking at a possible move. We'll call it move A. You start calculating down that branch, and you quickly see that if you make move A, your opponent has a response that completely crushes you. Checkmate N2.
All right, so move A is a disaster, a total dead end.
So, do you need to spend any more time calculating what happens after that disaster? Do you need to see all the different specific ways you lose your other pieces after you've already been checkmated?
No, of course not. I just need to know, don't do move A. That's it.
Correct. You snip that entire massive branch off the tree. You prune it. You stop searching it entirely. Alpha-beta pruning is just the clever algorithm for saying, I don't need to think about that bad move because my opponent is smart enough to see the obvious winning response and punish me for it.
So it works by assuming your opponent isn't an idiot.
That's the core assumption, yes. You assume optimal play from your opponent. And what that does is it allows the AI to ignore huge chunks of the game tree, all the garbage moves, which means it can use that saved computing power to search deeper on the branches that actually matter.
So it extends the horizon.
It clears the fog a little bit further down the road.
Yeah.
It makes the horizon effect less likely, but it never completely eliminates it.
Okay, so that's the world of games. Clean rules, clear turns, perfect information, a perfect little sandbox. But the book makes a big pivot in section 2. It says, logic versus the real world. Because the real world isn't a chessboard.
Not even close. And this is the history of what they call the logicist tradition. For a long time, early AI researchers, brilliant people, thought they could describe the whole world using strict Boolean logic. True or false, 1 or 0.
The example they use is the Wumpus world, which, again, I love that computer scientists act like these serious academics, but their classic examples are about a monster called the Wumpus.
It's a classic test environment for a reason. So imagine a grid of caves. In one of these caves, there's a horrible monster, the Wumpus. In other caves, there are bottomless pits. You're an agent, a little robot moving through these caves.
Okay.
And the logic rules are things like, if a square contains a Wumpus, then the adjacent squares are smelly. Or, if a square contains a pit, the adjacent squares are breezy.
Logic is very comforting. It's so definitive. I smell a stench, therefore the Wumpus is in one of these adjacent squares. It's like Sherlock Holmes. If P implies Q and I have P, then Q.
Ideally, yes. The grand hope was that if we could just write down enough of these logical rules, we could describe reality. We could build an AI that acts intelligently just by deriving logical conclusions from a massive rulebook.
It failed spectacularly from what I gather. Why? Why did that dream fall apart?
It failed because of the fog of war we talked about earlier, or what the text calls partial observability. In the real world, your sensors aren't perfect. You don't know for a fact that the Wumpus is there.
What do you mean?
Well, maybe your robot's nose is stuffy. Maybe its smell sensor is broken. Or maybe there's a dead rat in the corner of the cave that also smells bad. But it isn't a wumpus. You can't be 100% certain.
Right. The data is noisy.
The data is always noisy. And the book uses two terms here that I think are just brilliant explanations for why pure logic fails in the real world: laziness and ignorance.
And they don't mean that in a judgmental way.
Not at all, no. They are describing the problem.
Yeah.
Laziness refers to the fact that it is just too much work, it's computationally intractable, to list every single rule and exception for anything. Think about this simple rule. If you turn the key in your car, the car starts.
Seems logical. True.
Is it? Is it always true? What if a battery is dead? What if the starter is broken? What if you're out of gas? What if a squirrel built a nest in the engine block? What if a banana is stuck in the tailpipe?
Okay, I see your point. To make the logic actually true, with a capital T, I would have to write, if I turn the key and the battery is good and there's gas in the tank and there's no banana in the tailpipe, then the car starts.
And that list is infinite. You can't possibly list every single precondition. That's the laziness problem.
Right.
We just can't write it all down. Then there's the ignorance problem.
Which is?
Even if we could write down all the rules, we never have all the data. You don't know the state of the banana in the tailpipe until you get out and look. You have to act without knowing everything.
So strict logic, true, false, 10, it just crumbles under the weight of reality's complexity and uncertainty.
It shatters. And this brings us to the hero of the modern age of AI: probability.
This is the moment AI grew up.
It absolutely is. It stopped asking, is this true? And it started asking a much more useful, more nuanced question: how probable is this?
It seems like a subtle shift, but it changes the math entirely. Instead of a world of just 0 or 1, we're suddenly dealing with the entire spectrum in between, 0.7, 0.2, 0.99.
And the engine of this new probabilistic world is Bayes' rule. Thomas Bayes is actually on the cover of the textbook. That is how foundational this single idea is to all of modern AI.
Okay, we don't need to do the calculus on the air, thank goodness. But conceptually, what is Bayes' rule doing for the AI?
It's a formula for updating your beliefs when you get new evidence. That is it. That's the whole idea in a nutshell.
Okay, break that down.
You start with a prior, a baseline belief about the world before you've seen anything. Then you observe something, you get new evidence. And using Bayes' rule, you calculate a posterior, your new updated belief that incorporates that evidence.
The book uses a medical example, I think, a diagnosis.
Yes, the dentist example is a good one. Suppose you have a toothache. Old school logic might try to create a rule. Toothache implies cavity.
But that's not always true.
Right. It could be gum disease. It could be a sinus infection putting pressure on the tooth. You could have just bitten down on a popcorn kernel wrong.
So how does Bayes handle it differently?
Bayes says, okay, first, what is the prior probability of a cavity in the general population? Let's say it's low. Maybe 1 in 100 people have an undiscovered cavity right now. That's your baseline belief.
Okay.
Now, you show up with a toothache. That is new, strong evidence. Bayes' rule lets you combine the low prior probability of a cavity with the high probability that a cavity causes a toothache. And you get a new belief.
A posterior.
A posterior belief. The probability that you have a cavity, given that you have a toothache, shoots way up. Maybe now it's 0.6 or 60%. It's not 1.0. It's not a certainty, but it's likely enough to justify getting the drill ready.
There was also a taxi example in the notes that I found really, really tricky and counterintuitive.
Oh, that's a classic probability puzzle that trips everyone up. It's a fantastic example of how our intuition is often not rational.
So set it up for me again.
Okay, imagine there's a hit-and-run accident at night. A taxi was involved. You were a witness, and you tell the police you're pretty sure the cab was blue.
Okay, I saw blue. Logic says the witness saw blue, therefore the cab was blue.
But here are two other facts. Fact one.
Yeah.
You know that in this city, 90% of the cabs are green and only 10% are blue. Blue cabs are very rare.
Right.
Fact two. We take you into a lab and test your ability to identify colors at night under similar lighting conditions. And the test shows you are 80% accurate. You're pretty good, but you're not perfect. You get it wrong 20% of the time.
So, if I saw blue and I'm 80% accurate, surely the probability is 80% that the cab was blue. That seems obvious.
That's what you would think. That is exactly how human intuition works. We latch on to the 80% accurate number. But Bayes' rule says no, not even close.
Why not?
Because it forces you to combine the evidence from your eyes with your prior knowledge about the world, the fact that blue cabs are rare. Think about it this way. Because there are so many green cabs out there, the small number of green cabs that you mistakenly see as blue might actually be a larger group than the tiny number of blue cabs you see correctly.
Wait, run that by me again, even though I saw blue?
Yes, the math forces you to account for both possibilities. And when you run the numbers through Bayes' rule, the answer might be something like, there's only a 41% chance the cab was actually blue.
So it's more likely to be green, even though I saw blue with my own eyes.
It's wildly counterintuitive, isn't it?
It breaks my brain a little bit.
But it's rational. And that's what AI is trying to do. It balances the sensor data, what you saw, against the prior knowledge of the world, the statistics of the cab company. It doesn't trust your eyes blindly. It checks the statistics first.
This is a perfect transition to Section 3, perception, because we're talking about sensors. How do machines actually see? It's not just a camera.
Oh, not at all. This is one of the hardest, most profound problems in AI. For a human, vision feels effortless. It's instantaneous. You open your eyes, you see a coffee cup on your desk, done.
Right.
For a machine, seeing is an absolute nightmare of ambiguity and inference.
And the text calls this the ambiguity of vision. It uses an example that I think is just fantastic, the Godzilla problem. Please explain the Godzilla problem.
It's the core problem of projecting a 3D world onto a 2D surface. A camera lens takes a rich, three-dimensional world and flattens it onto a grid of pixels. In that process, you lose a ton of information, especially depth. So if the AI's camera sees a large, jagged green shape, is that a tiny toy lizard sitting 6 inches from the camera lens? Or is it a 400-foot-tall monster standing 3 miles away on the horizon?
To the pixels, to the 2D image, it looks exactly the same. The shape is identical.
Exactly. The geometry on the sensor is identical. Without context, without what the book calls an object model of the world, the AI cannot tell the difference between a toy and a city-destroying monster.
So how does it figure it out? The outline talks about deconstructing the image. What's the first step?
Before it can even figure out what the object is, the AI has to process the raw pixel data. And it usually starts with edge detection.
Finding the outlines of things.
Right. It scans the image and looks for sharp changes in brightness. If pixel A is bright white and pixel B right next to it is dark black, the AI says, aha, that's probably an edge.
But real photos are messy. There's noise, there's film grain, there's just imperfections.
A huge problem. If you just look for any brightness change, a single speck of dust on the lens looks like a tiny important edge. The image would be a mess of millions of false edges. So the AI does something really clever and very counterintuitive.
What's that?
It applies a Gaussian blur.
Like in Photoshop, you mean it blurs the image on purpose?
Exactly like Photoshop. It intentionally makes the image slightly less sharp to smooth out all that random noise.
Wait, hold on. It makes its vision worse in order to see better.
That is the beautiful paradox of it. It washes out the tiny, meaningless specks of dust so that only the strong, real edges of actual objects remain. It's essentially squinting its eyes so it doesn't get distracted by the insignificant details.
I love that. To see the world more clearly, the machine has to first blur its vision.
It's a trade-off between detail and signal. Then, once it has a clean map of the edges, it starts looking at texture.
And the book used the term texels. I hadn't heard this before.
It stands for texture elements. So think about a brick wall or a cobblestone street or even the pattern on your sweater. It's a repeating pattern. The book explains that AI uses texture gradients to judge depth and orientation. If you look at a long brick road stretching away from you, the bricks near your feet look big and far apart. The bricks way off in the distance look tiny and densely packed together.
The pattern squashes together as it gets further away.
Right. The AI can actually measure the rate of that squash. It sees the texels getting smaller and denser, and it calculates, okay, that part of the image is a flat surface that is tilting away from me at a 30-degree angle. It uses the texture to build a 3D map of the surface of the world.
So the goal isn't just to take a picture like tourist. The goal is reconstruction.
Yes, that's the key term. The AI is trying to build a coherent geometric 3D model of the world inside its head. It needs to know that the street is flat and the curb is a 6-inch vertical drop, so that if it's a self-driving car or a robot, he doesn't trip and fall on his face. It's constantly solving an incredibly complex geometry puzzle based on clues from light, shadow, and texture.
And doing it all largely with probability. It is probable that this change in brightness is a shadow cast by that tree, not a sudden change in paint color on the road.
Exactly. It's all just guessing. Highly educated, mathematical, Bayesian guessing.
Which brings us perfectly to the other main way we interact with the world, language. Section 4. And surprise, surprise, language is also a complete mess.
Language is arguably even messier than vision in some ways. In vision, at least, the laws of physics, how light travels, how optics work, are constant and predictable. In language, the rules are just social conventions, and they are fluid and constantly being broken.
And the source gives a perfect, simple example of this. He saw her duck.
Yeah, this is the classic duck ambiguity. It's a perfect example of why this problem is so hard for a machine. He saw her duck. Does that mean he saw a water bird, a waterfowl, that belongs to her?
Or does it mean he saw her physically crouch down to avoid, I don't know, a flying shoe?
Grammatically, both interpretations are perfectly correct. Duck can be a noun, the bird, or a verb, the action. Her can be a possessive pronoun, her bird, or the direct object of the verb, he saw her.
So how on earth does an AI know which one is right?
Context and probability. This brings us to a concept called n-grams.
N-grams. This sounds very technical, but it's really just counting things.
At its heart, it's just counting. An n-gram model looks at sequences of words. It doesn't understand them, it just counts them. It asks. In the vast amount of text I've been trained on, how often do these specific words appear together in this order?
Give me an example with the duck.
Okay. If the previous sentence was they were walking by the pond looking at the birds, the probability of the next word, duck, referring to the animal, is suddenly much, much higher.
Because pond and bird and animal duck all hang out together in the data, they have a high correlation.
Exactly. But if the previous sentence was someone in the crowd threw a rock, the probability instantly shifts. Now the verb duck is far more likely. The AI doesn't strictly understand what a rock is or why one might duck from it. It just knows that in its training data, the sequence threw a rock is often followed by duck as a verb.
This leads to the bag of words model, which is another image I just love.
It's a very powerful simplification technique. Imagine you take an email. You get a pair of scissors and you cut out every single word. You throw them all into a bag and shake it up.
You lose all the order. All the grammar is gone.
All gone. You don't know if cat came before dog, but you can dump the bag on the table and see what's inside. You see the words quince, Nigeria, millions, dollars, urgent, bank transfer.
Even without the order, I know for a fact that's a spam email. 100%.
Exactly. The bag of words model classifies a piece of text based purely on the frequency of the words inside it, ignoring the order. It's crude, but for things like spam detection or just figuring out the general topic of an article, it's surprisingly effective. It's purely probabilistic.
But there's a catch, isn't there? The source mentions a problem called data sparsity.
Yes, and this is a huge fundamental challenge. This is the problem of sentences that have never been spoken or written before.
Which happens all the time.
All the time. The book notes that even if you trained an AI on 1 trillion words of text, all the books, all of Wikipedia, the entire internet, there are still an infinite number of perfectly legitimate English sentences that has simply never occurred in human history.
Like, the fluorescent platypus thoughtfully considered the metaphysics of a good cheddar.
I am fairly confident that is a unique sentence in the history of the world. Now, if an AI relies only on having seen a sequence of words before to know if it's valid, it would fail in your sentence. It would look at fluorescent platypus and say, probability 0, never seen it.
But we know it's a valid sentence. Bizarre, but grammatically valid.
So the AI has to do something smarter. It has to generalize. It has to learn classes of words. It learns that platypus is a noun, fluorescent is an adjective, and it learns the general rule of English. Adjectives usually come before nouns. So even if it has never seen fluorescent platypus, it knows that the structure adjective plus noun is a very high probability structure in English.
So it's building a model of the language's structure, not just memorizing a giant list of phrases.
Right, and this ties all the way back to the very beginning. It's maximizing its expected success. It's making a rational bet that the new sentence it's seeing will follow the general patterns of all the old ones.
So if we step back now and look at this whole picture, we started this whole conversation with the idea of rationality over humanity.
Right, that AI isn't trying to be your friend. It's not trying to be human. It's trying to optimize a function. It uses search to navigate the future in these clean, perfect game worlds. But when the world gets too complex, too messy for pure search or pure logic,
It switches to probability.
it embraces the uncertainty. It has to. It uses Bayes' rule to manage the fog of war in its reasoning. It uses statistical blurring to manage noisy images. It uses n-grams and probabilistic grammars to manage messy, ambiguous language.
It really feels like the entire history of AI is the history of computer scientists realizing over and over again that the real world is much, much messier than they initially thought.
That is a really profound insight. I think you're exactly right. Early AI was, in a way, very arrogant. The logicists thought, we can write down the complete rules for the universe.
And modern AI is humble.
Modern AI is humble. It says the universe is chaotic and noisy and partially unknowable. I can't know the absolute truth. The best I can ever do is figure out what is most likely to be true based on the data